This video will begin talking about the next topic within this chapter, which is the one sample t interval for means. So we just did a one sample proportion, we did a one proportion interval, a one proportion z interval for proportions, and now we're going to switch over to means. So if you remember, on our reference sheet, we have the general formula for any confidence interval. It is right here, and it is of the format statistic plus or minus critical value times standard error of the statistic. So if you recall, with proportions, we did the formula for the statistic. We did, in symbols, we did p hat for the statistic, plus or minus. The critical value was z star, and the standard error of the statistic was the standard error of p hat. So if you recall, on the quiz that we just took, that was the formula for standard error of p hat off of the reference sheet, which was this one here, square root of p hat times 1 minus p hat over n. So now what we're going to do next is we're going to switch gears, and we're going to talk about what could be the formula for means. So instead of using the format with the statistic for proportions, what would it be for means? So if you recall, when we talked about our symbols, we talked about the statistic versus the parameter. Remember, the statistic estimates the parameter of the population. So for proportions, we said p hat estimates p. And for means, we said x bar estimates mu, where mu is the true population mean. So if you go back to this format then, when we go to the piece where it says statistic in our confidence interval, instead of putting that p hat in that first slot here, we're just going to change it to the symbol for the statistic for means, which is going to be x bar. So instead of putting our statistic as p hat, we're going to put x bar for our statistic, plus or minus. The critical value we're going to start with is still going to be z star. And then instead of writing here in the second slot, instead of writing standard error of p hat, because that's the standard error of the statistic, we're going to write the standard error of x bar. Standard error of x bar. Okay, so we now need to write the formula for the standard error of x bar. So if you look on the reference table, you see we just would have to scroll back to means. And we actually just came off of this unit very recently, and you guys know that it's used to be sigma divided by square root of n. Okay, but the problem is if we don't have sigma, we have to replace it with the sample standard deviation, which is called S. So I'm going to write that down. It's either sigma over radical n if we have it, and if we don't have it, it's going to be S over radical n, which is going to be coming up. Okay, so actually I should really write here sigma x bar. If I have sigma, I'm going to use sigma. And then if I don't have sigma, I'm going to replace it with S. So this is going to be the formula that we're going to do next. It's going to be the same steps of panic. We're just going to change it from a one proportion z interval to an interval for means, which we're going to talk about the name in a second. So here is the formula that I just generated. Statistic plus or minus critical value times the standard deviation of the statistic. Now, unfortunately, because we don't know the true value of mu, remember mu is unknown. Okay, this is the parameter and it's unknown. We don't know the true mean. We're replacing it with x bar, right? It's the statistic. So similarly, if we don't know the population mean, how are we going to know the population standard deviation? Sigma. Okay, see it's a sigma? That's the population standard deviation. If we don't know the population standard deviation, what we have to do is we have to replace it with the sample standard deviation, which is called S. So because of that, then there's some error present. And the error present now is going to be called instead of standard deviation, it's going to be called the standard error of the statistic. So whereas before it was sigma x bar equals sigma over radical n, okay, which is up over here. We don't have sigma, so we're going to replace that sigma, which is up here, with s. So now it becomes s over radical n, okay? So this is the sample standard deviation replacing the population standard deviation. But because it's estimating it, it's going to create some error. And because there's some error, that's why it's called standard error. Okay, so if you guys look on the reference sheet, that's what I was referring to here. Before it was called standard deviation, and now it's called standard error in this column. And that's why they're using an S over radical N instead of a sigma over radical N. Now, because of that, we end up having a new distribution. And basically the concept is this distribution winds up becoming a lot more spread out than the normal distribution. And the name of it is called the t distribution. So it is not quite normally distributed. It is still symmetric. So here's the picture here up over here. It's still going to look like a bell curve, single peak and bell curve, just like the z-score, but it's going to be a lot more spread out. The spread is going to be greater. So if it's more spread out, it's going to be wider and shorter than the z distribution. Okay. The t distribution is denoted by the number of degrees of freedom. Degrees of freedom is defined as the sample size minus 1. And I want to show you guys the t-chart to show you what I mean. So this is going to actually be called table B, which you have been looking at using your z-star. Go over to your table B now. This is table A. And here's table B. So if you look at table B, it says on the top, it looks like a bell curve, right? But it actually says t distribution, okay? The t distribution. And then what you see on this left-hand column, it says DF. And the DF are the degrees of freedom, okay? So it's a slightly structured differently than the Z table. Now, you know that on the bottom, we've been using that last row, and that last row is Z star. And now let me explain what's going on here. Since the degrees of freedom is equal to the sample size minus 1, as the sample size increases, the degrees of freedom also increase, because if n increases, the degrees of freedom also increases, because that's just sample size minus 1. So as you increase the sample size, what happens is the t distribution gets bigger, bigger sample size. It's going to become a smaller and smaller and smaller spread, and it winds up approaching the z distribution. So as you can see here, I have this red dotted line for the first curve. That's actually degrees of freedom 2, which means that the sample was size 3, because 3 minus 1 is 2. And then you see it goes to this blue, which is degrees of freedom of 9. That means the sample was size 10 for that one. And you see it's getting a little bit narrower and a little bit taller. And then when you go to the purple curve, that's actually the Z, or the standard normal. And that one is going to be the tallest and the narrowest and the least variable. So basically, as the degrees of freedom increases, the sample size increases as well. And the t distribution becomes, or approaches, I should say, the z distribution, which means it's becoming more normally distributed. All right. And that's why, if you look back on the table, that's why that last row is actually Z star, because if n approaches infinity, which it says infinity at the bottom here, the bigger the sample size, the more and more and more that this t distribution will become like the Z distribution. And that's why we use that last row that says infinity here. So the last thing that I want to show you how to do is find the critical value. Okay, so the critical value, you remember, if you go back to my interval used to be called Z star. okay? Instead of using Z star, we're going to change up our formula. And our formula is no longer going to be um, with a Z star. It's going to be with a T star. So I don't see my formula structure here. Let me just add it in. So the formula for the confidence interval now is going to be statistic plus or minus critical value, same thing, times the standard error of the statistic. It's going to be x bar, which is the sample mean, plus or minus, instead of using z star, we're going to use t star today, times the standard error of the mean. Okay? X bar is the sample mean. T star is what I'm going to talk about finding right now. This is the new critical value, and you can find it using table B. So if we look back at this previous thing, here's what you need to know. You need two things in order to find the T star. Looking back at my table, the first thing that you need is that left-hand column. You need the degrees of freedom. To get the degrees of freedom, we have to do sample size minus 1. Okay, sample size minus 1. So we need n. Then we need to get the degrees of freedom, df, sample size minus 1. So that is going to be your left-hand column over here. Then the other thing that you need is going to be the confidence level. So if you look on the bottom, you guys know we were given these different confidence levels. So let's say I wanted a 95% confidence level, and let's say I had a sample of size 20. I would do 20 minus 1, and that's 19. So I would go to 19 to this row for degrees of freedom, and I would go over, and then I would go to the 95% level, and I would look and see where they intersect. So I would wind up getting this T-star value of 2.093. That's going to be your critical value for T-star. Okay, so going back to this, we need two things. We need the sample size to get the degrees of freedom, and then secondly, we need the confidence level. And then you just line them up to get your T-star. So if you look down below at example 2, you guys try this example 2 right now and see what you get. Use the confidence level of 95% and use the sample size of 12. Find me the degrees of freedom and find me T-star. I'm hoping you looked at 11 for the degrees of freedom, 12 minus 1, and then 95%, and you got this value, 2.201. So that is the answer to T-star. Now, the other way that you might need to use table B is example 1. It says if the area to the left of the critical value T star is 0.90 and the sample size is 19, find the value of T star. So first we know n is 19. So we're going to do degrees of freedom equals 19 minus 1, which is 18. And then it says the area to the left is 0.90. So if we had drawn this picture, the area to the left would be 0.90 and the T-star would be over here. Well, interestingly enough, this reference sheet is actually for table B, it's the reverse of table A. It gives you the area to the right here highlighted. So it's the opposite of what we've been doing all year. So if you look here on the top, it says tail probability. That means that's actually the right tail probability that they give you. So if the area to the left is 0.90, the area to the right here will be 0.10. So if you wanted to find the T-star, you would look up the right tail probability of 0.10, and you would look up the degrees of freedom of 18. So right tail probability of 0.10, and then degrees of freedom of 18. And when you line that up, we get this value, 1.330. Now, something else to note about that is you could also look at the confidence level, but it's not 90. So I want to show you that. So if this was 10, then the symmetric area on the other side of the T-score would be negative T-star. So this would also be 10. So think about if this is 10 and this is 10, that's 10 plus 10 is 20, would mean that this middle chunk symmetrically would be 80. So that actually means the confidence level on that is 80. So if you guys look on the bottom of that T star that we just found, follow it down to the bottom, you see that the 80% is the confidence level associated with the right tail of 10%. All right, so that's really it for today.